Roberto on bag of gold microstates, please.
Okay, can you hear me? Yeah, okay. Thank you. Thank you. It's so far it's been a very exciting conference, and I've had lots of interesting and stimulating discussions, and I hope that it keeps this way the rest of the week. So thanks for inviting me. Well, what I'm going to be talking about is it's about microstates, but of a different variety, as we will see, very different from what we heard this morning from Joseph. One of my intentions here is to try to compare things and see whether we can connect different approaches or not. Okay, so part of what I'm going to say is based on a paper that we put out early this year with Ana Clement, my student in Barcelona, and then Javier Magán in Bariloche, Martín Sasieta in Brandeis, and Alejandro Vilar López, who's now in Brussels. But I'm going to give a broader overview of the entire subject of these microstate constructions. Okay, so it's not going to be only about this work, even if this one is the one where I think we've managed to put it in a broader framework. So, you all know this, and you all know that we also want to understand this from the point of view of microstates. Okay, so where are the microstates, or what are the microstates that account for this entropy? So, as Joseph already reviewed this morning, there was a big breakthrough in the field, 1996, when Strominger and Waffa managed to count a number of states that corresponded to a black hole in string theory, and the count of states reproduced on the nose the Bekenstein-Hawking entropy of the black hole. But the problem with that is that we're counting states that are not black holes. So this is a counting done in the weakly coupled string theory using d-branes. So we're counting non-gravitating states that are not black holes. So we get the number, but we don't know what states we have in the black hole side. And that's a problem, because we would like to know black hole microstates, proper black hole microstates, not states that would become microstates as we increase the coupling. We want to know what happens in the fully gravitating regime. And there are several reasons that we want to understand this better in the gravitating regime. There are some tricky questions, important questions, puzzling questions that with weakly coupled microstates we cannot address, or at least not in any obvious way. So for instance, there are aspects of the black hole information paradox and how information is recovered that we need to understand what's going on in the black hole geometry with a horizon, or with something that looks like a horizon. A closely related question is what's the experience of an infalling observer in a fully quantum black hole. Again, that's something that Strominger-Waffa states don't tell us much about. We also want to know to what extent the black hole interior is something that exists or not, and what happens at the singularity, or whether there's how is the singularity resolved in a full quantum theory of gravity? Where is it resolved? How much of the interior retains some measure of reality in a quantum black hole? Again, these are questions for which we need a better understanding of gravitating microstates. We need to understand physics at finite, that's non-perturbative, not infinitesimal, gravitational coupling. And this is something that string theory is not well designed for, because string theory is intrinsically defined as a perturbative theory, and then it's very hard to go beyond this, in particular if we want to understand what happens outside the supersymmetric regime. Yes. Yeah, please interrupt me, because if I don't get to the end, that's not a problem. I would prefer. Yeah.
Suppose you know the microstates, and suppose you know how to calculate at finite gravitational coupling. What do you need to compute in order to determine what is the experience of the infalling observer?
Well, I think I would like to know what the microstates are first. I don't think. Well, the answer to that question is going to depend on what the microstates are. because if they have very different nature, then yeah. I mean, you would need to have a probe, and then there are different kinds of probes. I don't want to talk about ADS-CFT. I mean, some of what I'm going to say will be using ADS-CFT, but we want more of a, I mean, ADS-CFT is good for telling us about the boundary description, but the bulk description is something that we don't know. And then infalling observers, they may come in different classes. There may be infalling observers or infalling things with a size and an energy comparable to that of Hawking quanta, and their experience may be very different of an observer who, I mean, it's some person, some student falling inside a very large black hole, okay? If it's a professor, it may be different, but okay. So what kind of microstate proposals we have on the table? There are several of them, but I think that the two most important ones, the ones certainly in this conference, the ones that are being more discussed, are on the one hand fastballs, which are visible horizonless, non-singular microstate geometries, well, non-singular at least with maybe small caveats, but the idea is that it's something that doesn't have a, well, the characteristic space-like singularity of the Schwarzschild black hole. Now, what I'm going to be talking about now is instead what I like to call a bag of gold microstates. And as we will see, these are microstates that have horizons and singularities. They also come with a number of strings attached, but I mean, it will be clear that in principle these states have smooth horizons and bad singularities. So these two approaches, they start from different, completely different points. You begin aiming in different directions. The methods are completely different, and the results are also very different. So one of the questions that I would like to understand better during these days is whether these two different approaches, they can meet anywhere, or whether they cannot meet, whether they are intrinsically different. And probably the best place to make contact is when we study BPS systems. But I'm not going to be focusing on BPS states today. Okay, I'm going to be talking about things in more generality. And as I said, in most of the talk, I won't be specifying ADS-CFT, maybe at a few points, but it's often useful to keep in mind the ADS-CFT perspective. But much of it goes through for situations where you don't have ADS asymptotics. Okay, so what's the starting point of this bag of gold microstates? So what's a microstate? How do we want to think of a microstate? A microstate should be some sort of microscopic pure state that's almost indistinguishable, at least for some simple observables, from the thermal state that corresponds to a black hole. Okay, so you measure, say, one-point functions or several point functions, and then this is something that, to a good accuracy, presumably exponential accuracy in the entropy, it's well reproduced, and at least for sufficiently long times, by the thermal density matrix that would describe your black hole. Okay, so if we want this almost indistinguishably hard distinguishability from a black hole, what can you do? Well, you go back to early days in, or at least I don't know if it was in the 60s or when Wheeler came up with the idea of a bag of golds bags of gold inside a black hole. The idea is that inside a black hole you can hide anything, or you can hide a lot. You can hide an entire universe, actually. Okay, that's something that for cosmologists that's familiar. This bag of gold, I mean, it's just some interior that you put at the other side of the Einstein-Rosen bridge. The exterior, you keep it unchanged. You have to put some matter to support it, but once you do this, then you can get you can put any arbitrary interior that almost any arbitrary interior that you have, that you want here. Okay, so the Penrose diagram. This is the this corresponds to this constant time, say the time symmetric slice of the black hole, of this geometry, and here you have some interior that, as I said, in principle you can design at your will. So, well, as I said, this has been known for many years, that you can have this. And as I said, this is obviously indistinguishable for at least from for simple observables from a black hole. So it's something that you can think as some candidate for a state of a black hole, because depending on what you have here, you can have different states, and since the exterior is the same as that of the black hole, this is something that well, you would need some fine probe, some quantum probe, in order to distinguish it from from the black hole, the conventional black hole that you would have. But the problem with this,
You have to go closer to the button.
closer to the thing. This, yeah, okay. Okay, the problem with this is that you can have I mean, it's the opposite of the problem with other microstates, is that you can have arbitrarily many of these, because say that you put here, you put some quantum state of matter, and then you put different quantum states of matter, each in an orthogonal state relative to the other, and then all of those states are going to be orthogonal, and then you can have a very large number of possible internal states. In principle, many more than what you would need in order to obtain the Bekenstein-Hawking entropy. So, one consequence of this is some version of the black hole information paradox, because if you can have arbitrarily many internal states, then you can entangle them with radiation, the exterior, and then this exterior can be entangled with an arbitrarily large number of interior states. And this is one version of the black hole information paradox, because this means that, for instance, the page curve need not go down or saturate when you reach the black hole entropy. Okay. So that's a problem. It's a problem that you're building too many states. It's, as I said, it's the opposite of what Joseph was describing this morning, that it's hard to get out of string theory, or at least with the methods that they were using, enough states to account for the black hole entropy. Here, in this approach, we're just at the other end. We have too many, and we have to do something with them. Okay. Now, for most of the yes.
Yeah. Can you prepare all of these states from non-singular initial conditions in Lorentz signature?
Okay. Yeah. I don't know how to do. Yeah. Okay. First. So, because I was. So you're saying whether I can get these things starting from. Well, in principle,
Lorentzian evolution starting from non-singular initial conditions.
Yeah, so I instead of having this, I could start with some pure state of matter, and the state of matter can be whatever I want, and then I make it collapse. I'm not going to get this because this is time symmetric, but I can start with arbitrarily large or arbitrarily many different states of matter outside, make them collapse into a black hole, and then try to see, those would be pure states, and they would correspond to, in principle, I think I can do that. I mean, it's not going to be the same as this, but they're going to be different internal collapsing geometries. This is a...
But they're presumably not arbitrarily many such
Yeah,
things.
it's not clear that I'm going to have, I mean, here I'm playing the game in such a way that I can have more. I'm not completely sure, yeah. Whether, I mean, that...
Almost certainly not in ADS.
That depends on, yeah. Let me see, because, I mean, of course, I mean, you're saying that, you're thinking that, I could imagine that I could, if I have enough volume outside, I can have many initial configurations that are going to evolve, and I can have. I think I can have that, right? If I have enough external volume, exterior volume, I can have a configurational entropy that can be as large as I want.
Yeah, that's why I was saying not in ADS.
So we're close to ADS, I think.
In ADS,
I mean, the ADS gas is
yeah, the
is
ADS
very
gas,
tiny
yeah, in
entropy.
ADS that's less clear that I can do that. In a central flat space, I can do it. If I have I can certainly do this for small ADS black holes, because I can make them as small as I want. For large ADS black holes, it's less clear that I can do that.
The graviton gas has a bound entropy.
Yes. Yeah. For large ADS black holes, it's less clear that I can do it. Yes. Yeah.
So what prevents matter to collapse toward the singularity, matter that is inside?
It's collapsing to the singularity. Nothing prevents it.
Okay.
Yeah. So it's these are. I mean, I'm going to be just like I could continue this into the singularity. I mean, this is just some interior cosmology. It's a crunch cosmology.
Okay.
I mean, that depends. So in principle, this matter can. Yeah. So in this other. In this other situation, which is what I'm going to be considering for simplicity for most of the talk, where I have two sides, the two-sided system. In this case, it's clear that this is starting in this is a big bang and this is a big crunch cosmology. Okay. So as I said, I'm going to be considering this, and I'm going to consider this sort of double-sided bag of gold. Okay, so this is something that it's. I mean, the idea is not new. The idea of constructing and then counting this kind of microstate, it goes back a number of years, certainly to a paper by Kurkulu and Maldacena, who did it explicitly in SYK and JT. Much of the work that was done later was also in 2 dimensions. Then more recently, there's been more work on how to extend it to higher dimensions. And then, lately, we've been doing it in higher dimensions with charge, rotation, and other properties. Okay, but there's more people here that I'm not including. So how do we work? Because we want to do something that's quantum gravity. What quantum theory of gravity am I going to be using? I'm going to be using the gravitational path integral, which, as you all know, it's something that's notoriously ill-defined. It's as ill-defined an object in physics as you may wish, but nevertheless it turns out to be able to play some magic in very surprising ways. So the gravitational path integral, which the Euclidean gravitational path integral, as it was introduced by Gibbons and Hawking, something that naturally wants to construct Hilbert spaces of states in gravity. And we'll see, I will describe this in more detail later. So it allows you to define quantum states, and not only quantum states, but also to construct the products, the overlaps between different states. Okay, but with a twist that is important, that it's actually not computing this, but this with an overbar. This property that the GPI, the gravitational path integral, kind of is wanting to construct Hilbert spaces. That's something that's been emphasized in recent years by Don Marolf and Henry Maxfield. It's an effective tool. It's not something that depends on ultraviolet detail. It actually works without being completely oblivious to the existence or not of an ultraviolet completion to your theory. But nevertheless, it is a tool that, even if it's effective, it's not very well defined, as far as we know, as far as we can define it. But it's surprisingly powerful, and also comes with a lot of intriguing peculiarities. So, what are these bag of gold states, which for short I'm going to call the bogs? If we have a swampland, then we can also have a bog. Okay. So one of the things that we have is that, this is a fully gravitational picture. Okay, so we don't have this problem of the Strominger-Vafa initial construction, that it's weak coupling. This is fully gravitating. The constructions that we're going to study are extremely universal, and as I will try to argue, they apply in the case where you have charge, rotation, supersymmetry or not supersymmetry, and whether you can have also quantum corrections to your states. So it works in all of these cases. So it's very universal. And of course, the fact that it's universal is good, but it also means that it's hiding a lot. But one thing that will follow very clearly from the construction is that these bag of golds, they are never orthogonal to each other. the gravitational path integral always gives you overlaps between different box. Okay, so they are not independent states. And then, well, in some cases, you can even count the dimension of the Hilbert space of states. And this is something that can be realized within ADS-CFT, but the basic idea is more general than this. So I'm going to begin with something very basic. I mean, many of you already know this from kindergarten, but people have gone to different kindergartens here. So I'll go to, well, first slow, how we can define quantum states using path integrals, first in quantum field theory and then in gravity.
Are you going to mention how bag of gold states can be constructed in ADS-CFT?
Yeah.
Okay.
To some level of detail. I mean, if you ask me for a lot of detail, then the discussion can get more complicated, but yeah. So, well, I mean, the path integral, the Feynman path integral in the Euclidean signature is something that allows you to compute transition amplitudes. I'm going to be working always here, at least, in Euclidean signature. And you know, well, this is an integral over field configurations. You integrate over all possible field configurations that interpolate between an initial field configuration and a final configuration, and this is giving you this matrix element. You evolve it for some Euclidean time, you get that. Then one thing that you do, I mean, that was transition amplitude. You can construct states by a formal procedure which consists of cutting open the path integral. So you leave this unspecified. This corresponds to this ket. Okay, so you evolve it for some time, leaving this unspecified. And you can also construct the bra, and well, the product corresponds to gluing them and summing over all possible configurations in the intermediate configurations. Okay, so this is how we construct products between states. We can also consider thermal states. For this, we take configurations that have imaginary time periodicity, so we take the initial and the final configurations to be the same after some Euclidean time evolution of length beta, and this is what's computing the trace over of the exponential of the Hamiltonian. Okay, so that's the thermal density, the thermal partition function of the system. And well, once you have this, you can also construct, you can cut open this path integral, and what this defines for you is what's known as the thermophile double state, where you have one state here, you have your Hilbert space consists of a product of two Hilbert spaces, left and right. You evolve for half of the periodicity beta, and this is a maximal entangled state between the left and the right Hilbert spaces. Okay, so I imagine that many of you are familiar with this. Yeah, spacebar, okay. Now, how do we do now this in gravity? Okay, this is what Gibbons-Haugen introduced. Here I'm drawing something that might correspond to the de Sitter space. You have the Euclidean cigar geometry that corresponds to the Schwarzschild or Schwarzschild ADS geometry. You take a periodicity to be beta. Now, this is topologically a disk times a sphere, so I'm going to draw it as a disk. This is the Euclidean horizon, which is just a sphere here, a point in the plane and a sphere in the full space-time. And we, if you want, if this is ADS, then we also have the boundary where we have the dual field theory, where it's defined, where it lives. Okay. So, as I say, this object is not well defined, very well defined, but we can compute it in the semi-classical approximation around saddle points. And everything that I'm going to be saying, it's always, and we're always going to be working with semi-classical saddle points. If you're in low enough dimensions or with supersymmetry, then sometimes you can go off-cell and consider configurations away from saddle points. But yeah, I'm just going to focus on saddle points. So we can take that same path integral that we had before on the disk, we cut it open, and then this defines the gravitational version of the thermophile double state, which corresponds to the thermophile double state of the dual field theory. Okay, so we get here state, this is S2 times an S2, so this is a picture of the kind that we were drawing before. Now, this state, this is a Lorentzian state. If we, since this is a time-symmetric slice, then we can continue it in Lorentzian time. The Lorentzian evolution of this state, I mean, this is something that you may think as some tunneling process. The Lorentzian evolution is giving you the upper half of the Penrose diagram. Yes?
Yeah, can I just see the previous slide again for a second? Yeah, this
That's a second.
one. No, the next one.
You asked, yeah. Yeah, this one?
Yeah, so I always had a
No, but you
confusion
said
about
just
this.
for a second, so I showed it only for a second. Sorry.
Yeah.
That's silly. Yes.
So I've always had this confusion, so maybe I thought I would ask again. If I look at that cylinder at the bottom,
Yes.
the cylinder generates a state on the two circles, on the union of the two circles, right?
So the cylinder, that's the boundary, okay?
That's the boundary, yeah.
Yes.
So it generates a state on the union of those two circles. On the at
On
this circle and that circle.
Yeah, so this is a state that
Yeah.
entangles the left part of the boundary and the
right part.
Yes.
So you get an entangled state which lives on two circles.
Yes. On two, spheres. Yes.
Yeah, two spheres. But it's very important in this picture, those two spheres are not connected. They're not touching each other. There's no Hamiltonian interaction. They are just, if I just look at that state, it's entangled but not interacting.
Yeah, I mean they are disconnected. You could also have in some situations you can also have some black holes where they are side to side. I mean
Okay, so that's the part I was worried about, because now if you go to the next slide,
yes.
so if I look at the first figure and the left and right
So this
parts of
is
the first
this.
figure,
Yes.
okay,
They
so
live
there is,
in different
so they're not
asymptotic
interacting.
regions. They are not
Right.
interacting. Yes.
But when you draw their corresponding, when you try to fill in the inside bulk, at the center point where you draw a little cross,
Yes. This one. Yes.
yeah. So there are two different theories. One where you take the left and the right
Yes.
sectors and you don't join them, and one where you do join them. And I always thought if you take the dual to the guys which are not interacting, it'll correspond to a bulk which is not joined in the middle.
So, but that in that case, so I'm not sure where you're going to, but in that case, if there's no connection, then you don't have any entanglement between the two, right? Is this what you're?
Okay, so I was just
So
saying that
this is what the
not
gravity
dual.
is giving you if you just follow your nose with the gravitational path integral, and that you look for the saddle point that satisfies these boundary conditions.
Okay, so maybe we should do this offline, but I would actually question this step. So, but we
Okay.
can do this offline.
You would
yeah.
question this? Okay,
Yeah.
good. Yeah. So this is well, as I said, what this is telling us is that the thermophile double state in gravity, I mean the dual of the thermophile double state of the CFT, that corresponds to the eternal ADS black hole. Okay, that's the picture that was proposed by Juan Baldesena more than 20 years ago. Maybe you have objections to this, and I will be happy to discuss them. But I'm going to take this at face value. Okay, so we construct this in Euclidean, and then we have the Lorentzian evolution. In here, this is completely non-singular, but the Lorentzian evolution develops a horizon and a singularity. Okay, and that's going to be a property of all the states that I'm going to be considering. Because this is just taking this as a state. It's the thermophile double state of the CFT. It's the thermophile double state of my gravitational theory. So it's a state, okay? It's one something that you could call, it's a microscopic state. And then I can construct more states. Just like I had this state, this is one state. It's a pure state of the full theory. It's entangled between left and right, but as a state of the full theory, it's a pure state. And I can construct other pure states, more pure states. How do I do this? Well, I can insert matter. If my theory allows me to have matter, that I can put in the black hole interior, then, well, this black hole interior, I can make it there, I can make it self-gravitate and grow an interior in the black hole. And the way that this is going to evolve when I go to the Lorentzian geometry, well, this is the Euclidean geometry. I have this matter, this kind of this matter that's stretching my interior. It's creating this bag of gold, and the full Lorentzian geometry is like this. It's one of the geometries that we saw before. Okay, so this is a large space-time inside the black hole. It's a bag of gold. It's, as we were saying before, it's an interior cosmology that begins in a crunch and ends. No, it begins in a bang and ends in a crunch. Okay. So this is an example of how we can construct these box states using the Euclidean gravitational path integral. We can prepare them by inserting this matter. Yes.
Is there a mathematical criterion on the volume in the interior that would make you say this is a bag of gold, as opposed to, say, the volume in this room, which is not sufficiently large to make a bags of gold?
Okay, not a local criterion. Well, I mean, if our universe, I mean, we could live as far as we know, we could live inside a black hole, large enough black hole that this would be our Big Bang, and then if our universe ended in a, I mean, imagine that we don't have a cosmical constant, or it's something that dies away, and that our universe ends in a crunch. So in principle, I mean, that could be, this could be our universe, something like our universe.
But I'm trying to ask, how large do you want the volume to be in
I
order
want it
for
to
you
be
to
very
call it?
large, so I can, if I put a large amount of matter here, then I create a large amount of space. Essentially what is happening here is that the more matter that you have here, you can, I mean, the way that this is compensated, because the exterior remains the same. This has a finite mass. You can put an arbitrarily large amount of mass in the interior of the black hole if at the same time you're creating an arbitrarily large universe inside. Because if you want, the negative gravitational energy compensates for the positive mass that you're introducing. You want positive mass. We're not violating energy conditions here, but yeah, I don't think that there's any other condition. So out of this bag of gold microstates, a class that's particularly first simple to work with, and also one that will allow us to have a complete calculability down to the end when we want to count states, is that we're going to consider that the matter that we have is some shell of dust of some matter M. Okay, and I want this shell to be sufficiently heavy that it creates a large enough interior. This is not a test shell; it's a fully gravitating one. Okay, so when I do this, I've taken that matter that I had before, compressed it into just a thin shell, and then I'm creating, well, a bag of gold that has this kind of geometry, this shape. Okay, in ICFT, that's your question. This is something we know that creating particles of dust in the interior, we can achieve it by introducing, say, some scalar operator with some dimension. The dimension of the operator is going to be related to the mass. I'm going to consider a large number of them. This doesn't need necessarily mean that my operator dimension has to be large. I can have a large number of these particles. But yeah, well, I mean, this is going to be some operator inserted here at the boundary of ADS. Okay. And that's the picture that, if you want to think in terms of ADS-CFT, that's the picture that I'm going to have in mind. So, okay. Moreover, I'm going to take the limit where this shell is also very, very heavy. That's going to be very convenient, because in this case, the shell remains all the time close to what would be the boundary of the space. Of course, the boundary here is cut off, but this is something that's very far from the center of the black hole. Okay. So in this case, I'm creating a large interior volume, and this shell trajectory, it's, as I said, it's almost independent of whatever structure I have here. Okay, and this is going to be crucial for universality later. Okay. So now that I've introduced these states, I'm going to now do calculations with them. I've constructed a large number of them. Can I compute products between the states? Well, in order to compute products, as we were saying, this is what is giving you the ket. The bra is the state inverted, and then you have to glue them. So what I'm interested in computing is the matrix of state overlaps. And that's a gram matrix, if you want, of states that we have, and I want to compute this matrix. And well, if I have two states, or a state, I mean, if the bra and ket correspond to the same state, then I can do this, and this is computing the norm of the state. I mean, the state initially wasn't normalized, so this is computing the norm of the state. But if I have states corresponding to two different, say, two different cells, they may carry different quantum numbers, or their masses can be different, then in general, at least at the leading semi-classical order, I don't have a saddle point corresponding to a connection between them. Quantum level, I can have connections, but those are going to be suppressed when in the semi-classical limit. So then two states corresponding to two cells of different masses, they are going to be orthogonal to good accuracy, to exponential accuracy. So I'm going to have, this means that I can construct an infinite family, because I can have these cell masses to be arbitrarily large. I can have an infinite family of orthogonal states. If I have an infinite family of orthogonal states, then this means that my Hilbert space has infinite dimension. And this is the problem of bags of gold that we described earlier. That I mean, we began constructing the gravitational path integral seems to be giving us a way of constructing quantum states in gravity which are just too many. Okay, so that's the problem. But well, the problem is solved if we now add on top of the rules that we've introduced for the gravitational path integral, we add a rule which is natural, that we can also consider, when we're computing these products, we can also consider configurations that connect the same boundaries, but maybe in other ways, in non-trivial ways, through non-trivial topologies. So if I want to consider, say, this, the product of these two matrix elements, then, well, I have here, I have the kets, I have here the brass, and well, if I connect this one to this one and this one to this one, then I get 0 times 0, and that's in principle what I would say would be the result, because each of these matrices, matrix elements is 0. But if I now consider, if I now take a look and then see that I could also connect this one with this one and this one with this one in this way, so I have one boundary and another boundary, so this is a wormhole connecting two different boundaries, then in this case, well, there's no problem connecting this with this and this with that, so I get a non-zero result. So even if this matrix element was 0, the product of two matrix elements, that's non-zero. And that's why I'm putting here a bar over here, because the way to interpret this now is in terms that the gravitational path integral, what's computing is the average of these products. Because if in general, if I have that this matrix element is 0 when I is different than j, but the square of this matrix element is non-zero, then the natural way to interpret this is that this is not computing this quantity, but the average over some ensemble. So there's no problem in a quantity being 0 and its square being non-zero if that quantity corresponds to some average over some ensemble. And the gravitational path integral is not telling us what the ensemble is. Okay? It's just giving you this result, and then you say, well, this is indicating to me that gravity is not computing just the exact matrix products or matrix elements, but the averages of them. Okay? So wormholes are a way of knowing, when we introduce the wormholes, we're also introducing this averaging in a necessary way. Okay? And this is something that it's a very general argument. This I can do for any bag of gold. So if I had a bag of gold made of some matter here, and this could be a shell of or whatever you have, and the other bag of gold constructed with some different kind of matter, I can always construct this wormhole, okay? Which is telling me that the two states, any two bags of gold, are never orthogonal. There's always a non-zero overlap, statistical overlap between them. Now, if I have these heavy shell microstates that I described before, the ones that correspond to cells that are moving all the time very close to the boundary, then this is something that gives me a lot of calculational leverage, because this, you see that this quantity that I would compute in order to to obtain the normalization factor. In this case, this is something that simplifies a lot, because this is almost an entire disk and another entire disk. So up to a factor of the shell that factors out and will cancel when we take a normalization, then what I get is that this normalization factor is essentially the product of the, each of the gravitational path integrals, the partition functions taken on each of the separate black holes. And the shell does not affect the properties of the horizon. So this is something that is going to give us universality of the construction, that the dependence on the shell will drop out when we normalize everything. This is temperature. I'm here introducing chemical potentials because all of this goes through. This could be chemical potential, it could be rotation. If all goes through, essentially because the shell is just a small perturbation over, or a small, gives a small contribution to all of these products. Okay, so in particular, when we consider these heavy shell wormholes, we can compute what is this, the product of these two matrix elements. And it's when you take the normalization, all the contributions from the cells, they factor out here and they cancel with the normalization. Okay, so this is the result of this. You can call this the moments of the gram matrix, and it takes a very simple result in terms of something that here, this is just this partition function over these disks with these boundary conditions, and the cell properties, they've dropped out. This is for a two-boundary wormhole, but I can also consider higher boundary wormholes. If these cells are very short, I can have an arbitrary, if this cell trajectory, the Euclidean cell trajectory, is always very close to the boundary, then in this case, I can put an arbitrarily large, I can construct arbitrarily large number of boundary for this multi-boundary wormhole. So I can compute all of these moments of the gram matrix to arbitrarily large numbers. And the result is very simple. You can very easily show that in this case, this is the general result for an n-boundary wormhole, and it depends only on the black holes of the properties of the black hole, the exterior black hole. The bag of hole, the interior, doesn't affect any properties. We only have the parameters of the black hole that we're studying. Now, all of the things that I've been describing, I haven't been saying it. I've been always working with canonical or grand canonical in general boundary conditions. Now, if I want to count the microstates of a black hole, then I want to work in the microcanonical ensemble. I want to count states within some microcanonical window, narrow window. Well, the way to do this, in this case, we can take, say, essentially an inverse Laplace transform for going between these moments computed in the grand canonical ensemble and the microcanonical ensemble. I can do this and not say anything more, but I'm going to say that if I do this, so all of this was constructed for geometries. All the geometries that I constructed were microstates in the grand canonical ensemble. When I do this, this trick, I'm also losing track of what is the geometry of a microstate, of a microcanonical microstate. That's something that I don't know what it is. So that's something that one should bear in mind. In the BPS case, since all the calculations are always done on the BPS surface, then that's not a problem. But outside, away from the BPS limit for non-extremal black holes, then the microstate geometry becomes less clear what it is for these microcanonical states. Thank you. Yes.
Can you go to the previous slide?
Yes. No,
okay,
this is not the previous.
There was a slide where you presented the result for yes, this.
Yes.
This. When you're writing this equation, do you have in mind a single wormhole, fully connected contribution that gives this result? I'm worried about the possibility that other wormholes contributions.
Yes, there are other possible wormhole contributions. In many cases, you can argue that those are subleading.
Like, for instance, ones that connect only a part of the copies, and other copies are disconnected.
Yeah.
And you're saying these are subleading?
So I think, let me see. I think that they are subleading. Yes, in the semiclassical limit. Yeah. If you're saying JT gravity, then you can consider their contributions, and then you can add them all up. But I think these ones they are the subleading.
Thank you.
Yeah, subleading. Okay. Now, well, here you see also that here out of this, when we go to microcanonical, we get here a factor of A over 4G. Here, I mean, I'm not interpreting this as any entropy. It's just something that the gravitational path integral is giving you. Okay. I mean, the wormhole, or
yeah. So this thing, I mean, can I scan it as a tunneling between? I mean, this is a wormhole which has multiple.
It's a wormhole. It's a Euclidean solution that's connecting systems with different boundaries.
But if I have two different, can I see this? If I have one shell and
you want
another shell,
to see this as some real time? I mean, something that I can continue to real time and then considering
like a tunneling probability, for example.
Well, I mean, it's giving you some matrix element.
If I have two of them, if I just have two of them.
No, but that's the way that I've constructed it's, I mean, if I have two of them, say, for instance, this one, or, yeah. This is the square, if you want, of a matrix element. It's not a probability. It wouldn't be a probability at most.
In the canonical ensemble, yes.
Yeah.
But if I go to the microcanonical
to the microcanonical ensemble,
I see your last formula. That looks, I mean,
yes.
The factors look to be exactly right.
Yeah, I mean, yeah. So in other circumstances, you would say that this is giving you the probability of tunneling
between one shell and the other one. Is that would that be correct? I mean, I don't know. My understanding of the things is quite limited. So
let me see whether that could be.
Only have two of them, just two of them. So
yeah, just two of them. Yeah, just like this one.
But the microcanonical version. The formula you have in the microcanonical.
Yeah. I'm not sure whether it's appropriate to interpret it as tunneling probability. I imagine that maybe. Yeah, in the case of two of them, I think that you can do that. Yes. If you have more than two, I don't think that you can do it.
Sure, that's a mess.
But for two, yes, you can do it. Yes.
Because then this gives you exactly the same answer as in the Krauss-Matur estimate. So, you know, the Krauss-Matur estimate is, you know, when you tunnel one fastball into a black hole or into microscale geometry, there's a tunneling and, you know, there's a e to the minus 4 times a and so on. So, you know, you get exactly the same.
Well, but in that case, I mean, you get, I mean, the probability.
They're estimating it using something else.
Yeah,
so
no,
they're
but
estimating the probability to make a fastball out of a shell.
So if you do that calculation, if you do it in the canonical, then you get half of the probability. I mean, this is the problem that you were mentioning before, earlier this morning, that you don't get the factor that would cancel the...
But here, do you get the factor which would come in?
Here, well, first, you're getting the factor of 2 because of the fact that you're double-sided, which I don't think that in the case that you're talking about you would have. And this is a probability where you have, I mean, it's a different configuration. It's not just because the one that you were saying, that it's the one that would correspond to the
shell.
Single
shell popping up.
But I mean, the probability that you're talking about would be the case It would be the usual Gibbons-Hawking partition function, right? Not this one.
I don't know.
Yeah, I think it's a different one. I think it's a
okay.
different one.
Thanks.
Okay. So let me make some remarks about these states. So as I said, we're losing track of what is the geometry in the microcanonical microstate. This is something that we can keep. We can have a better control when we're in the BPS sector, because that's microcanonical. Also, the complete, if I want to have this semi-classical analysis of overlaps that allows me to have all of these moments to arbitrarily large order, large moments, then I need multi-wormhole geometries with a weak interaction. What this means is that not all possible kinds of matter that you put inside the black hole are going to do to be good for this, and you also want to avoid interactions between matter interiors. So for this, these very heavy thin cells, those are convenient. Other kinds of matter are not good for performing a complete analysis. They are less calculationally useful than the heavy cell matter cells, or heavy cell dust cells. Okay. So now that we have the states, we can do the counting. I'm not going to go into full details of this, because that's not the point. But at least I'm going to give you an idea of how we can count the set of states that we have. So we've constructed these states. We've seen that they have non-trivial overlaps between them. So if we want to count the dimension of the set of states, well, that's going to be the rank of the matrix that we constructed, the Gram matrix. But, well, black hole microstates, as we've seen, well, they give us that this matrix is diagonal. So in principle, if we just took this, the rank of this matrix, of course, is just infinite if you have an infinite set of states. What we want to is, well, a different way of counting this dimension. The technique for doing this, and you can compute what is the rank of a matrix, not just by doing the, say, you could do it if you had a Gram-Schmidt diagonalization, but another way of obtaining the dimension of your Gram matrix is by computing the moments of the distribution of products of the matrices. And well, I skip this. This is giving me a. So the way to do this, so as I said, we have statistical moments. The statistics is forced by the introduction of wormholes. So there's a technique that's familiar in random matrix theory, which computes the density of states out of properties of this object that's called the resolvent matrix, and that was used in this context by Pennington and collaborators in a famous paper. But what I just want to say is that you don't need to know the individual matrix elements. What you need to know is the moments of the matrix, and out of this you can recover what's the dimension of the rank of the matrix. When you do this, when you use the moments that we computed before in the microcanonical ensemble, then you get that the dimension of the Hilbert space is given by this number. Why do you get a factor of 2 here? This is because we're considering the two-sided black hole. So we have two CFTs. What this is counting is the total number of or the total number of states that the two CFTs have. So that's why we get we have two CFTs, and that's why we get twice the black hole entropy. Now, this procedure that I've explained to you is something that gives us, more generally, I would get area over 4 here if I begin with a theory of Einstein gravity. If I begin with a theory that's Einstein gravity, say, plus corrections, it's going to give me, that's going to be the corrections to the black hole entropy as well. And this is here, I mean, this is an object here. I mean, I got A over 4, okay? A over 4 is what Gibbons and Hawking would tell us that it's the correct entropy. But here I'm not using the gravitational path integral in the same way as Gibbons and Hawking used. I've used it to construct states, to construct a Hilbert space of states, to count the dimension of this Hilbert space of states, and it comes out. It gives me the same value for the entropy as Gibbons and Hawking would do using their black magic of the gravitational partition function. So it's not a circular argument. This is my point. Yes?
When you compute the dimension of the Hilbert space,
yes,
this maybe you can write it as some like rank of the density matrix, yeah, and you will basically have to show that the variance of this observable is 0.
No, the variance is not 0.
Okay, but then
in the supersymmetric case, there's a paper by Ellis and the others where they show that in that case it's 0, but here the variance is not 0. So I'm computing the dimension with a variance.
Okay, so it's like the average dimension of the Hilbert space.
Yes, yes.
And do you know?
That's why I'm putting here an overbar.
Yeah.
Yes.
And do you know how large is the variance?
Well, the variance is order 1. I mean,
okay, so it's exponentially
it's
suppressed.
Exponentially suppressed. Yes.
Thanks.
So these heavy cells, as I said, they can be constructed for rotating charged black holes near extremality or at extremality or supersymmetric or not. You can include the quantum corrections, the log A and log T corrections as well. You can include also effects from higher curvature theories. They all give you automatically the same result. Essentially, because the cell is very far from the horizon, so it's all the effects of the cell just drop out. Okay, so in all cases you get the right result. So I'm going to come to my conclusions now. Of course, what I've told you is that the result is very universal. As I said, universality is good and bad. I mean, it's just it's something very similar to the universality of a Gibbons-Hawking original calculation of the black hole entropy, because it's something that works for almost any gravitational theory. If you have Einstein theory of gravity or some different variant, any higher curvature theory, it would also work. It gives you the entropy of the black hole, but it also gives you the result for theories that may not have an ultraviolet completion. It works for theories which are in the landscape, theories which are in the swampland, theories that may have pathologies. So it's something that it's good and bad. It just gives you everything without telling you any more details. Okay. Now, we've used the gravitational path integral here, and as I said, it's an effective tool, but we have to make up the rules, because we don't know how to derive in principle, and it would be nice if we could derive the rules for the gravitational path integral, whether you have to include some configurations or others, from some microscopic theory. These rules for how to compute the products, something that we're making up. Now, can we derive this from some microscopic theory? Well, as I say, from perturbative string theory, that seems to be difficult. If we want to go non-perturbative, probably we have to rely on the CFT. But then that would amount to, well, I mean, it's very, I mean, it would be deriving properties of the bulk from the ADS in properties which are highly non-trivial. Okay, so that's something that would be very interesting to do if we could obtain better understanding of how to obtain these rules. Now, some more final or concluding remarks. One of them is that we've introduced wormholes. What are wormholes from this perspective? Wormholes are the way that gravity knows that the Hilbert space of states of a black hole is finite dimensional. If we had introduced the wormholes, then we would get an infinite dimensional space. But the wormholes also, the way, I mean, you introduce them, they tell you that you have a finite dimensional Hilbert space, but they also introduce this randomness, this averaging, this intrinsic randomness. And there's this intriguing property that a semi-classical black hole geometry, in this case, seems to need, if you want to get microstates that admit a good semi-classical black hole geometry, You need some sort of randomness, probably also some chaos. And it's unclear whether this is just a property of these constructions or whether this is something more general. Whether, if you want to have smooth geometries or not, whether it's necessary if you want to have a smooth geometry, whether you're necessarily be performing some averaging over some ensemble or not, or whether something beyond. Is this everything, all that we can learn from semi-classical gravity, or everything that we can do for the microscopics of black holes, or can we go beyond? And that's, well, I'll leave it here, and then, well, thank you for your attention. But that's... That last comment goes in the direction of can we connect this to other kinds of microstates, other constructions of microstates, and I would like to, well, hear your opinions. Yes.
Stupid question, but when you build these bags of gold states, and
Yes.
what is the continuity conditions that considered as solutions going across the horizon? You build some interior state. Is it what is the is it a solution?
So this the matter never goes through the horizon.
Okay, when you build a universe inside a black hole, you can't make it analytic across the horizon. So what are the continuity conditions?
So let me see. I'm not sure whether. Yeah. So let me see.
So,
So that I have one of them. Yeah. Like this one. Okay. So the horizon is here.
Yep.
This is just.
But if I analytically continue Schwarzschild, I just get Schwarzschild interior. I don't get anything else. So
Oh yeah. There's
So-
some.
so what is the
yeah.
kind
So that's. But this is analytic to. I don't know to what order, but it's.
okay, this pertains to the fact that a long time ago, Joseph and I realized you could start building microstate structures inside horizons, but you would
Yeah.
sacrifice.
Yeah, you sacrifice some analyticity, definitely, but at least you have a C2.
Okay, so
C1,
then you
C2.
can fill the thing full of microstate structure to your heart's content. You can do our construction inside horizons as well, as long as you sacrifice.
So if you I mean, analyticity is, of course, is something that I'm willing to sacrifice because I don't think it's a physical criterion.
Right.
Okay, so that's what I'm sacrificing here, and then I'm putting, yeah, that's what allows me, if I insisted on analyticity, then none of this would go through, but analyticity is not it's not a must.
Yeah, so you can build lots of microstate geometries inside horizons.
Oh, yeah. You can put here, you can put, for instance, strings. You can put, any of your microstates. Well, I mean, they are going to be time dependent. That's what makes this harder. If you, well, I mean, the way that these things are constructed in the supersymmetric case is that first you begin with non-supersymmetric geometries, and then you take the, you project to the ground state by taking the temperature to 0, the beta, the periodicity beta to infinity. But you begin constructing them as non-supersymmetric ones. So I'm not sure whether like this one, I mean, this kind of things inside there, yeah. I'd be interested in knowing how this would work. But the supersymmetric states, this kind of supersymmetric bag of gold states, you begin with something that's not supersymmetric, and then you project to the.
I see.
the
No, the
ground
ones you
state.
have, I mean, it's a very stupid idea that you take an R4, R3, and then you put another R3, and you
Yeah.
put on the second R3 you put a multi-center solution.
Yeah, I
And then,
see,
you know,
yeah.
on the second R3 you have a -1 in the harmonic function, which at some point is going to beat you
Yeah.
up. But if you put a lot of solutions, you can just put lots of stuff there, and
Yeah.
you can just build them. You have to give up analyticity up to, like, you know,
Yeah.
if you kill, I mean, you know, if you insist to L infinity, then, you know, of course you
Yeah,
cannot build
yeah,
anything.
yeah,
But
no,
if you give me, you know,
yeah,
any up to L 10,000, I can build solutions with
Yeah.
a symmetry.
yeah. Yeah, okay. I'd like to think a bit more about this, yeah.
You had a slide where you represented the thermophile double state as a half disk,
Yes.
and then you mentioned this connection of two half disks in
Yes.
order. But I'm confused by this step. I thought that the Euclidean signature describes only the exterior of the black hole. It is as if you are trying to connect two
So this
different.
is what.
But before this slide,
Before.
like you had the TFD yes, yeah. The next one, I think, the TFT, and then the two. Yeah. This, yeah.
Yeah.
On the right picture, it seems that you are trying to connect two exteriors of the black hole, because in the Euclidean signature, the
Well, I'm
cigar.
connecting two exteriors in the same sense that this is connecting two exteriors to the asymptotic regions.
I'm confused how you are creating the interior region in the middle.
By putting matter. This is the bag of gold trick.
Okay.
It's putting. I mean, you put matter and then you expand the interior automatically.
Final question, quick question. Okay, so then let's thank Roberto once again.